Hello everyone, in today's session we're going to demystify conducting emission tests. Okay, often we receive a conducting emission test report such as this one, for example, and in the test report they often tell you, okay, pass or fail, and if it fails, at which point they failed. And it is quite easy to understand the lower frequency performance since each emission you measure is strongly related to the switching frequency of your product. But often what people are not so sure is what we call a hump shape, often in a higher frequency range. So for example, in this particular case, between 10 to 30 megahertz, there is a hump. And this in electronics engineering or in EMC engineering is called a resonance phenomena. And in today's session, we're only talking about this resonance phenomena. We're going to discuss what caused this resonance, what can change this resonance, and most important of all, how can we relate this hump resonance which we observed in the frequency domain to the time domain. Okay, so let's start. Okay, so this is the test setup, very basic as we often use for our education purposes. We have a automotive license set up, and this is just a Texas Instrument evaluation board. This is a flyback topology doing step down conversion at the moment. Here we have a quiet electronics load. That means this one does not introduce noise to the overall measurement. Now, one of the things you may ask, and actually lots of people ask, is like, Min, when we set up, for example, in this case, if we want to set up a automotive CISPA25 conducting emission, why the standard says that the cable length has to be less than 20 or 30 centimeters long? Why do we need to have this insulation support? Or in other words, if we had a longer cables, what kind of effects will it bring? So in this case, let's demonstrate. Okay, so as you can see here, we start with a short wire connection. So this is perhaps, according to the standard, this would meet the standards because it's quite short. Okay, so we have a short wire between the DUT and the listens. And in this case, we're using a receiver, okay, a tech box receiver for this work. So this receiver is basically controlled by the software. Okay, so let's just get on the software. So I'll just quickly show you. Being a receiver, it has, of course, the EMI analyzer function. It also actually has a oscilloscope, which is quite handy, and we'll use this to analyze the time domain performance. But for now, spectrum analyzer, click that. And I'm just doing a scanning between 100 kilohertz all the way to 100 megahertz. Okay, so I can start the scan, and it's a real time, so it's very, very fast. So currently, as I haven't switched on the unit, so all I measure is the noise floor. Okay, so now we're gonna switch on the converter and then see the noise profile. Okay, so as you can see, the scanning is very, very fast. The moment I switch on, is all the results is here, and this is in its FFT mode. That's why it is very, very fast. Okay, as I said, in the lower frequency range, you can easily identify these as the switching frequency of the converter. So in this case, I think it's 130 kilohertz, and we all know that, right? So 130 kilohertz, then you've got the second harmonics, third harmonics, fourth harmonics, and so on. What we're interested is this, isn't it? As you can see, this is from 10 megahertz, 20, 30, 40. So we have a resonance peak at 40 megahertz, as 40 megahertz. Okay, so now if I stop this result, right, and then I can save this, what I'm going to do next is I'm going to change a longer wire and then show you the impact. So let's do that. All right, so you can see I changed the wire to be a much longer cables, okay, and nothing else. So on the scanner, I also saved the previous results. So this color represents the previous results, and I'm gonna test this new results based on this longer wire and see the impact. Okay, so again, let's just do a continuous sweep. Right. Okay. So you can clearly see the comparison between the two. Okay, So in terms of the lower frequency performance, I don't see much difference, perhaps 1 dB difference right there. But what is interesting is you can see that the resonance peak shifted from 40 megahertz to 30 megahertz. So that is interesting because it means that the wire length actually can shift this resonance frequency. So what's been going on then? Well, in order to demonstrate resonance, let's start from the very basics. Here, listen. This is a resonance phenomena, right? This is an audible resonance. And think about the difference between an audible and electronic resonance phenomena. They are essentially the same. So in order to make a sound, for example, at a wedding, I want to make an announcement, I would hit a glass, right? And then this basically makes a resonance sound that everybody can hear in the room. In order for this resonance to happen, therefore the sound can propagate, we need two things, two conditions. First, what we need is a resonance structure. So in this case, it's the glass, okay? The glass itself is a resonance structure. And second condition to meet is that I need to hit it. Not only do I need to hit it, but I also need to hit it with some power. If I hit it very gentle, you can see it's not really resonant. However, if I hit it hard, you can hear the difference, right? So really, it's the same principle. For an electronic circuit to resonate, we need two things. First is the resonance structure. So in this case, the resonance structure is formed by the DUT, which is in this case is the PCB. The structure, right? We've got long cables. We got some parasitic capacitance between the PCB and the test ground plane. And also, we got listen. And the listens are basically just some L and C components. So as you can see, we have the cable wires, of course, you can treat it as inductance. This is capacitance. So the whole circuit is an LC circuit. So naturally, we have an LC tank circuit. Now next is, how are we going to hit the circuit with energy? Well, in this case, is the switching device. And in this case particularly, it's not really the switching frequency that matters, right? Similar to the phenomenon that we hit the glass, it's really how hard you hit it. So how hard we switch the device really depends on the rise time of the switching event. So in this case, if the rise time is small, meaning we have a hard switch, then the circuit can resonate quite efficiently. Okay, so going back to our short wire, now let's have a look at the resonance phenomena, but in time domain. So I switched it on. Of course, it's back to where it stands previously. So again, we have a 40 megahertz resonance. And now some people were struggling to correlate this 40 megahertz phenomena to how the circuit or how the setup behaves. Well, most of the design engineers, we are familiar with time domain. So in this case, let's quickly switch to time domain and see what happens there. Okay, so I'm going to the oscilloscope mode. So this is the beauty of this machine. It allows us to analyze a circuit from both the time domain and frequency domain. So let's have a look. So if I click continuous, so again, I'm measuring exactly the same point, which is the listen receiver, right? So I connect the receiver to the listen, but rather than looking at the frequency domain, I'm looking at the noise in time domain. So I believe I can zoom in. So we understand that if you measure between this point and this point and this point, you will measure probably 130 kilohertz, which represents the switching frequency. But this is interesting. This is the resonance we talked about earlier on. So I can, for example, zoom in horizontal. So now, this definitely is a resonance phenomena in time domain, of course. Now you will be interested to measure the frequency of this. So let's have a look. We can add a marker line. Add marker line. Okay, there we go. We got a marker line, we put in here. And we got another marker line, or you can do V delta. That's great. So I can put a delta right next to it. And here it shows me the difference between these two peaks is 25 nanoseconds. 25 nanoseconds. What is 25 nanoseconds in frequency range? 40 megahertz. 40 megahertz. So that makes sense. That means that 40 megahertz resonance peak we've seen previously in the frequency domain really means a 40 megahertz ringing in the time domain when we measure in the LISM. In fact, if you clamped a current probe as a common mode method on these two wires, you will measure exactly this 40 megahertz ringing in the common mode current. And that is how we correlate the time domain and frequency domain. Okay, hopefully this short version will demystify this resonance hump in your conducting emission test, and see you next time.